Okay, let us start by recalling what we saw in the previous video. We have already come across the notions of linear combination and linear span. So if you are given some vectors, some finitely many vectors in a vector space V, then their linear combination is an expression that looks like this. Where the alpha i's are, of course, scalars coming from the underlying field. If a non-empty set is given to us, which is a subset of the vector space, then the linear span of S denoted by L of S is defined to be the set of such linear combinations where the vectors are coming from the set S. Note one thing, that the set S itself may be infinite, but when we consider linear combinations of elements of S, in one such combination only finitely many elements will be there. That is because linear combination is defined only for finitely many vectors. We are not saying that when we are defining L of S to be the set of all linear combinations of elements of S, then that does not mean that you can take infinitely many elements of S and form their linear combination at once, because that is not defined. That's not what linear combinations are. Linear combinations, any one such combination at a time involves only finitely many. So that is one thing. After defining this, we saw that this L of S turns out to be a subspace of the vector space V. But we in fact extended this definition to include the case where S is empty by defining Li of S. We devised a notation like this. The way we defined this Li of S is this. Li of S is the intersection of all subspaces of V containing S. That is, you collect all subspaces of V, each one containing S. There may be some subspaces of V which do not contain the set S. By the way, this Li of S is not defined just for the case when S is empty. It's defined for any subset S of V. This restriction now is not there, that S has to be non-empty. S is any subset of V. For any such subset, we have defined Li of S to be the intersection of all subspaces of V containing the set S inside of it as a subset. There may be some subspaces of V which do not have S as one of its subsets. We don't consider them. We collect those subspaces of V which have S inside of them and then take their intersection. That intersection is Li of S. After defining this, we then prove that if S is non-empty, then our newly defined, we call this one also linear span. This turns out to be equal to actually L of S, the old linear span. And we also saw that when S is empty, then the linear span, that is linear span, our new linear span of the empty set is the set consisting of only the zero vector, which we know is a subspace. In fact, it is the smallest subspace of V. So we see that in this case, in this special case also, our new linear span is a subspace, and when it is a non-empty subset S, then of course Li and L coincide, they become the same thing. So in that case also it's a subspace. So for any subset S of V, our new linear span is again just like L of S, it is also a subspace. It's only slightly different from this in that it is also defined when S is empty. Then after having these things, we saw this lemma that if S and T are some two subsets of V, then these facts are true. If S is a subset of T, then the linear span of S is a subset of the linear span of T. Linear span of the union of S and T is the sum of their linear spans, and the linear span of the linear span of S is the linear span of S. Instead of proving this, we stated another lemma, another similar lemma, where instead of this ordinary L, we have our new linear span. Note that the author did not mention that S and T are non-empty subsets explicitly. That's because for the author, L of S is defined only for non-empty subsets. So wherever you see L of S, it's automatically assumed that the underlying sets of which we are taking linear span, they are non-empty. So here S and T are non-empty. Here, however, in our new lemma, S and T are any subsets. They are allowed to be empty also. We have already proved this. We, however, were not able to prove this satisfactorily. I mean, I messed up somewhere in between. I think in trying to show that this is contained in this. So we start from here. So you can understand that 1 has already been proved and half of 2 has been proved. So I start the proof like this. We have, so because we are going to prove 2, let's just write 2. We have already proved that Li of S plus Li of T is contained in Li of S union T. This one is easy. You can apply you can apply part 1 and the fact that S and T are both subsets of S union T. So that will give you the proof. Now the converse, the reverse inclusion. Next, we prove this. The inclusion, that is this thing that we want to prove, is trivially true if at least one of the sets is empty. For example, if you take S to be the empty set, then here you have Li of t. On the right hand side, Li of S means Li of the empty set, that is the zero space. If you add that zero space with Li of t, you get Li of t. So in fact we get equality in that case. So assume that both S and T are non-empty. We in fact came this far in the previous video, but after that we messed up. Not you, I messed up. Let us first handle the special case where S and T are actually disjoint. There is no common vector. They are disjoint. They have empty intersection. So we start by considering a vector V in Li of S union T. Note that because S and T are both non-empty, so S union T is also a non-empty set. So by what we already proved back then, this is equal to the ordinary linear span of S union T. In brackets we can write, note that S union T is non-empty. Don't confuse this thing with this thing. Okay, this is the intersection and that is union. So because now V belongs to the ordinary linear span, so V will be a linear combination of some elements of S union T. Then let me continue from there. Then V is equal to, say, lambda 1 V1 plus lambda 2 V2 and so on, lambda n Vn, where the scalars are coming from the underlying field. F is always the underlying field when only one field is involved, that is understood, and the vectors are coming from S union T. So each vector can either be in S or T, but not both. That is because S and T are disjoint. So a few cases will now arise. If all the vectors are actually in S, then this linear combination belongs to the linear span of S, and hence this belongs to linear span of S plus linear span of T. Why? Because L of S is itself contained in L of S plus L of T. To see that, you consider any element in this subspace. You can write that element as that element plus 0, the 0 vector, and that 0 vector belongs to L of T. And note that because both S and T are non-empty, assume that both S and T are non-empty, so L of S is Li of S and L of T is Li of T. Similarly, if the vectors all belong to T, then their linear combination will belong to the linear span of T. And hence P belongs to L of S plus L of T, which again is Li of S plus Li of T. So now one more case is there, that all the vectors are not in S and also all of them are not in T. Okay, let's write this case like this. Now assume that neither S nor T contains all the VI's. You say I and T intersection this B W1 W2 Wj. So these are the vectors, these are the VI's which belong to S, and these are again some VI's which belong to T. Note that although we are writing U and W, they are after all nothing but those VI's. So we have classified them into two disjoint sets. I plus J is N. Now or we can write then. You can clearly see that V can be written like this. Oh, but we will lose track of the Wi's, no? I mean, sorry, the lambda i's. We won't know which lambda comes with which one. So for that, let us continue to write them as V's, but Vi1, Vi2, Vi say j, and here again some other Vi's, V say k. I hope I haven't taken k here somewhere. Even if I have, you can understand what we are writing here. K1, Vk2, Vkl, say. So it just simply means that if you collect these subscripts I1, I2, etc. to ij, and you collect all the k's, k1, k2, etc. to kl, and you take the union of those subscripts, you will get the set of positive integers from 1 to n, and these two sets of subscripts are disjoint. There is no common subscript. So that's how the corresponding Vi's are also disjoint. Now V can be written as lambda I1 Vi1 plus lambda I2 Vi2, etc. lambda I j Vij plus lambda k1 Vk1 plus lambda k2 Vk2 plus etc. plus lambda kl Vkl. Clearly, this linear combination belongs to the linear span of S, because the vectors involved here are coming from S. Like that, the second one belongs to the linear span of, it belongs to, okay, linear span of T. And again, because S and T, both of them are non-empty, so this is Li of S and that one is Li of T. Okay, so in any case, either when all the vectors are in S, or when all of them are in T, or when that is not the case, V has been shown to belong to this. Thus, in any case, we have V belonging to this. Hence, Li of S union T is contained in Li of S plus Li of T. Okay, but keep in mind that this itself is also coming from a case, coming from some restriction, namely when S and T are disjoint, but they may not be disjoint, they may have some intersection, there may be some common vector. So what do we then do? And in fact, let's just mention that here also. Hence this, when S and T are disjoint. Now we handle the case where S and T are any subsets. Any subsets, but of course we have already handled the case where at least one of them is empty. So that for those cases, those trivial cases, the original containment itself is always true. Okay, so there is no need to consider them. We can in fact here also, when S and T are not necessarily disjoint, we can consider them, both of them, to be non-empty. Be any non-empty subsets of phi. Fine. By what we proved above, we get Li of S union T equal to Li of S minus T union S intersection T union T minus S. Which we already know. S union T can be written like this, and one more thing we know is that these three sets which are subsets of S union T, they are mutually disjoint. So this will be, you can apply this containment, this one 2 times. T minus S, and again you apply that here. Okay. Now note that S minus T is, we already know what S minus T is. S minus T is the set of those vectors in S which are not in T. And we also know that this set is a subset of S. So because it is a subset of S, by part 1, this is contained in the linear span of S. This is also a subset of S, and in fact this is also a subset of T. Anyway, we can consider any one of them. Say this is a subset of S, and because of that this is contained in the linear span of S. and this one t minus s is a subset of t. So by part 1, this third term is a subset of the linear span of T. Now here we are adding a vector space with itself, because after all Li of S is a subspace of V, so it is a vector space itself. So this will be equal to Li of S, these two things, and the last one is Li of T. So in this general case also, where S and T are not necessarily disjoint, we have proved that this is a subset of this. Hence, combining the already proved reverse inclusion with this, we get equality. Thus, so that completes the proof of part 2. Now we go to part 3. One half of part 3 is very easy, since S is contained in the linear span of S. Part 1 implies that the linear span of S is contained in the linear span of the linear span of S. Okay. Since linear span of S is a subspace, we have already seen that this is a subspace. In fact, it's the zero space when S is empty and is nothing but our ordinary L of S when S is non-empty, and L of S we have already proved that it's a subspace. So that's why this is always a subspace. Subspace of our vector space V containing itself we have this inclusion also true. How? This thing is by definition the intersection of all subspaces of V containing Li of S, and this is one such subspace of V containing Li of S. So that's why naturally this will be contained in this, because here we are taking all such subspaces and their intersection, and this is only one of them. Hence, so you consider the linear span of a subset once, that is enough. Again, if you take another linear span, you don't get anything new. So this completes the proof of our lemma that we have written. But what about the original lemma? How can we prove the original? Note that we have not proved the original lemma 4 to 2. So we now go back to that, but we are not going to write anything as a formal proof. We will just see how the statements in lemma 4 to 2 follow from these things that we have proved. What are the statements? Number one, so now S and T are non-empty subsets of the vector space V. The first one says that if S is a subset of T, then L of S is a subset of L of T. What we have proved is this: if S is a subset of T, then Li of S is a subset of Li of T. But because S and T are non-empty, this is nothing but L of S and this is L of T. So that's how number one, part one follows. In part two, we consider L of S union T. We have to prove that this is L of S plus L of T. Because S and T are non-empty, their union is also non-empty. So this is nothing but Li of S union T, which according to what we have proved already, Li of S plus Li of T. And again, you can write Li of S as L of S and Li of T as L of T. So that gives you part 2. In part 3, something similar happens. Because S is non-empty, so the Li inside is L of S. And we already know that L of S contains S as a subset. So L of S is also non-empty. Non-emptiness of S implies every superset of S is non-empty. So again, that implies this outer Li is our ordinary L. Okay, so this is one thing. And what about Li of S? Li of S we have already seen is nothing but L of S. And we have proved just now that these two things are equal. So correspondingly these two things are also equal, and that is the third part of our actual lemma 422. So that's how we have the proof of lemma 422 also as a consequence of this concocted lemma, the lemma that we have made. So let us now go to a new definition. And this is the definition of finite dimensionality. The vector space V is said to be finite dimensional over F. If one wants, one can throw in that part over F. If there is a finite subset, S or finite set S in V, S of V such that L of S is equal to V. So this definition says that if you encounter a vector space in which you find a finite subset S such that the linear span of S is the entire space, then we say that the space V is finite dimensional. And the definition makes sense also. It tells us that in a slightly loose manner, that a finite dimensional vector space is a space in which finitely many vectors have the power to generate the entire space. In that sense, the space is not very large and unmanageable. It is somewhat manageable. Okay, so in that sense, V is finite dimensional. Note one thing, that this definition defines finite dimensionality, not the concept dimension itself. That is something that will come shortly, okay, that will come later. Right now, the definition only says that when a vector space can be generated by some finite subset inside of it, then it is said to be finite dimensional. But the author has used the ordinary linear span. We are going to, just like how we have been extending the other things, we are going to extend this one also. So let us write a corresponding definition. The vector space V is said to be, okay, do we really need this corresponding definition? That's what I'm thinking. The only thing that will be, oh, okay. Now, right now we don't need this. We will see why. If we want, we can extend this definition. You know how? By using not L but Li. However, that will not actually give us anything new. Okay, we will, in this definition itself, everything has been covered. It may seem like the case S equal to empty set is being missed here by the definition, but that is not the case. We will see. Right. So after this, what does the author have to say? Note that Fn is finite dimensional, where F is some field, of course, and n is a positive integer. This is because Fn is the linear span of S where there is a very special and natural S which one can guess that generates Fn. to see how this set, I should not say generate, but spans, that is the technical term. To see how the vectors in S span the entire Fn, a general element in Fn looks like what? It's an n-tuple of field elements, so it will look like this. Where the xi's are of course coming from the field F. Keep one thing in mind, that these ones and zeros that you see here are not necessarily real numbers 1 and 0. They are field elements. This is the additive identity in the field and this is the unit element in the field. You can see pretty easily, considering the operations in Fn, addition and multiplication by scalar, that this vector can be written like this. Plus xn times this n-tuple. So any element in Fn appears as a linear combination of these vectors. So clearly every element belongs to the linear span of this particular S, and the linear span of S of course is also contained in Fn because it's a subspace of Fn. So because of this, Fn is finite dimensional. Note that the definition requires you to find at least one S. You find one S, that's enough. You don't have to look for any other S or anything. Once you find a finite S, then that tells you that the vector space is finite dimensional. But sometimes it happens that no finite S is sufficient to span the entire space. Then it becomes not finite dimensional or infinite dimensional. After this, the author, yes, he says this itself that we were mentioning back then. Although we have defined what's meant by a finite dimensional space, but we have not yet defined what is meant by the dimension of a space. So that will come in due time. We, however, move on to the next thing. Next, there is a definition. Now here comes the next extremely important definition of linear dependence and hence correspondingly in independence also. Okay, they have presented it in this way. Let V1, V2, etc. Vn belonging to V be some vectors finitely many we say that these vectors are linearly dependent over F if these following conditions are true. Are linearly dependent over the field F if there exist scalars that is field elements, an equal number of scalars. Not all of which are 0. This is the crucial part of this definition. Not all of which are 0, such that the linear combination formed using these things is the 0 vector. Let us see what this definition says. We are given some vectors in a vector space, finitely many, keep that in mind. We say that those vectors are linearly dependent over the field F if there exists an equal number of scalars, not all of them 0 simultaneously, such that this linear combination is 0. Okay, because if you want such a linear combination to be 0, one easy choice is to consider all the scalars to be 0. That linear combination is trivially 0. However, here we demand that not all the lambda i's be 0. At least one has to be non-zero. If such a choice of scalars can be made, not all of which are 0, for which the linear combination is 0, then we say that those vectors are linearly dependent over F. And here we are going to again define a corresponding extended definition, where we no longer consider finitely many vectors, but in fact any collection of vectors. So this is definition star. These starred items are things that we are introducing extra. Let S be any subset of the vector space V. We say that S is linearly dependent or the vectors in S are linearly dependent. In that way also we can say this. Are linearly dependent. I need ink. Give me a moment. We can mention over F since we have mentioned it there. If there exists some finitely many vectors in S which are linearly dependent according to the previous definition. So in this new definition, which is sort of an extension of that one, we are using that one. Okay, so here we are saying that a set S of vectors in V will be called linearly independent, or the vectors in it will be called linearly independent. Sorry, so what the hell am I saying? Dependent, not independent, okay? Dependent. A subset S of V will be called linearly dependent, or the vectors in it are called linearly dependent if we can find some finitely many vectors in S that are linearly dependent according to this definition. That means for which we can find an equal number of scalars, not all of which are 0, such that the corresponding linear combination is the 0 vector. So here S itself can be an infinite set. Okay, that does not matter. If we can find some finitely many vectors in S that are dependent in the usual sense, then S is also called dependent. And now we say what we will say when this is not the case. When they are not dependent, then they are called independent. If the vectors are not linearly dependent over F, then they are said to be linearly independent. Over F. Just like that, if a subset S of the vector space is not linearly dependent over F, then we say that S is linearly independent over F, or the vectors in S are linearly independent over F. There are multiple ways of saying the same thing. Here too, okay, now some simplification in writing. Here too, we shall contract linearly dependent over F like linear combination over F. If F is understood, we don't write that over F part. Here also we won't write the over F part if that is understood. If it is understood where the scalars are coming from, then we don't mention the field. To just simply linearly dependent. And if you want to be very informal, we will see sometimes when it becomes slightly cumbersome to keep writing linearly dependent, linearly independent, we often simply write dependent and independent, because in the context of the things that we have here, dependent and independent, they are linearly. Okay, we are not studying dependence or independence of vectors in some non-linear way. Everything is done linearly. Non-linearity does not appear here because there is no multiplication of two vectors or any such operation like that. If you just simply think of linearity in the usual way we think of it, like having a linear equation is having an equation where the variables occur in their first power. Say this is a linear equation. This is a non-linear equation, something like that. And now some easy consequences of these definitions. Note that if some vectors are linearly independent, then none of the VI's can be 0. Why is that so? That is because if you, for example, take V1 equal to 0 and you don't know what the other VI's are, then you have this choice of scalars that will give you a 0 vector. That is, you take lambda1 equal to 1 and all the other scalars you take them 0. Then for such a choice of scalars, this linear combination is clearly the 0 vector, but at the same time all the scalars are not 0. Zeroness of V1 allowed us to choose lambda1 non-zero, and that is why these vectors are linearly dependent. So that means if some vectors are given to us and it is given that they are independent, then none of them can be 0. Okay, independent vectors are by their very independence non-zero vectors, and then something else is also true. One more very easy consequence of these definitions is this. Also, note that the empty set is linearly independent. Why? According to our extended definition, the empty set first of all is a subset of a vector space. No, it's a subset of any vector space. For this to be dependent, we should be able to find some vectors in the empty set that are dependent. Okay, for the empty set to be dependent, we need some such vectors to exist inside the empty set which are dependent according to the original dependent independent definition. This, however, is not possible simply because the empty set is empty. So lack of such vectors makes the empty set not dependent, that is independent. So that's what we have written. The empty set in any vector space is always independent. Now some non-trivial examples. In F3, F is any field, we can easily see that these vectors are linearly independent. How? That means there exists no choice of such scalars that gives you the zero vector, but at the same time some scalar being non-zero. That is not possible. To see that, what you do, you consider such a linear combination. And set that equal to the zero vector in the space, and then see what happens to those scalars. You can see that the linear combination gives you the 3 tuple this. By the definition of equality of 3 tuples ordered triads, all of them must be equal to 0. So we see that you cannot choose the lambda i's in such a way that not all of them are 0, but at the same time the linear combination, not all of them are 0, but at the same time the linear combination is 0. Such a choice is not possible, because for the linear combination to be 0, it's necessary that all the scalars are also 0. Okay, so that is why they are linearly dependent. Whereas these some other vectors linearly independent. I am getting confused between linearly dependent. I am not confused. Inside my mind I am thinking the correct thing, but sometimes independent is coming out in place of dependent. You can understand what I am trying to say. Okay, if you are following it quite minutely, in R3, in our ordinary 3D space, these vectors are linearly dependent. 1, 1, 0, 3, 1, 3, and 5, 3, 3. So here some such choice of scalars exists where not all the scalars are 0 but the combination is 0. You can see pretty easily that if you multiply the first vector by 2 and the second one by 1, do we get the third one? 2 plus 3 is 5, 2 plus 1 is 3, and 0 plus 3 is 3. So that means in this case two times 1 comma 1 comma 0 plus 1 times 3 comma 1 comma 3 plus minus 1 times 5 comma 3 comma 3 is equal to the 0 vector in the space. And here in fact all the scalars are non-zero. So that's why these vectors are linearly dependent. If you want to include the field in this saying, linearly dependent over R. Okay, now we come to one point. Why do we keep calling over F? What happens when the field changes? Does linear dependence and independence, like the notion of linear combination, also depend on the underlying field? Yes, it does depend. So this example shows what can happen when the field changes. Linear dependence and independence depend on the underlying field of scalars. Consider the field C of complex numbers. We know that this is a vector space over itself, just like every field is a vector space over itself. And also this is a vector space over the field of real numbers. Any field is a vector space over any of its subfield. The vectors one and I, this I is your imaginary unit, square root of -1, in C are linearly dependent over C but independent over R. Changing the field changes their status. Dependent over C but are linearly independent over R. How? They are dependent over C because of this equation where you treat this one and this I as vectors, these vectors, and the other coefficients 1 and I as scalars, because the underlying field of scalars is also C itself. So there are complex numbers available for you to choose as scalars. Note that this is your lambda 1, this is your lambda 2, this is V1, this is V2. Lambda 1 and lambda 2 are, in fact, both of them are non-zero, but the linear combination is 0. So over C, 1 and I are dependent. However, if you choose some, say, alpha 1 and alpha 2, real numbers, if now your underlying field of scalars is the field of real numbers, then this equation implies that both alpha 1 and alpha 2 have to be 0. Why? Because now this equation is your it says that the ordinary complex number alpha 1 plus alpha 2I is equal to 0, where alpha 1 is the real part and alpha 2 is the imaginary part. And from the definition of equality of two complex numbers, we know that this is true only if and only if both alpha 1 and alpha 2 are equal to 0. So the possibility of choosing non-zero scalars that we had here is not present here. Here both the scalars have to be 0, only then the linear combination is 0. So over C, dependent over C, but at the same time they are independent over R. So it really matters what the underlying field is. That is why in such confusing situations where you can have two different things, it's better to write that over F part. Okay, now what are these notions of linear dependence and independence good for? Why have we defined them? So we will now see what they lead us to. So we start with this somewhat elementary but very important lemma 4-3. If V1, V2, etc. up to Vn belonging to a vector space V are linearly independent, Here there is only one underlying field, so we don't bother writing over F. Okay, so we will omit it sometimes. Then every element in their linear span has a unique representation. Has a unique representation of this form. Is the author? Yes, lambda. It does not matter what symbol we use, but it feels nice to write exactly what's written in the text. With the lambda i's coming from the field F, of course. So this lemma says that if we are given a number of vectors, finitely many vectors that are linearly independent, okay, not dependent, independent, then you can consider their linear span L of this set. In that linear span, every vector looks like this. That we already know. Okay, in fact, that comes directly from the definition of the linear span, but something else is true. This representation is unique. That is, for a given vector, these scalars are uniquely determined. You cannot get for a given vector in the linear span of these vectors having two different representations like this, where the scalars, I mean, you can have more than one choice of scalars. Such a thing will never happen. So let's see the proof. Let phi belong to the linear span of these vectors. Then, by the definition of linear span, P is expressible in this form. For some scalars, that's all. Okay, so far we haven't said anything about linear dependence or independence, so we don't bother whether these scalars are zero or some of them are non-zero or all of them are non-zero. That thing has not come yet. Now we want to prove that these lambda i's are unique. So suppose there are some possibly different scalars mu n belonging to F such that P is also expressible as a linear combination of those same vectors, but with these scalars mu2 v2 mu n vn. then lambda 1 minus mu 1 v1 plus lambda 2 minus mu 2 v2 plus lambda n minus mu n vn is equal to using the elementary properties of a vector space, we can write this expression as lambda 1 v1 plus lambda 2 v2 etc. plus lambda n vn minus mu 1 v1 plus mu 2 v2 etc. plus mu n vn. Both of these things are equal to v, so this is 0. So this linear combination of the vi's has become 0. Now we invoke the condition that the vi's, the given vi's, are linearly independent. So because of independence, you cannot have non-zero scalars that make this linear combination 0, because otherwise they will be dependent. So independence now implies that all the scalars must be equal to 0. Since these are linearly independent, we must have lambda I minus mu y equal to 0 for all I varying from 1 to n. That is this completes the proof, because it shows that the lambda i's are the only scalars. There cannot be any new scalars that will also give you the same v. So this representation for a given v is unique. The next theorem, although very easy and at first glance, these are the author's words. The next theorem, although very easy and at first glance is of a somewhat technical nature, has as consequences results that form the very foundations of the subject. So the next theorem is very important. Although looking at the theorem itself, it will not be apparent that it is very important and fundamental, but the consequences of the theorem themselves are of such importance that the theorem itself becomes important. So let us see what that is. If v1, v2, etc. up to vn are in some vector space V, then either they are linearly independent or some vk, that means some v among this is a linear combination of the preceding vectors. Yeah, linear combination of the preceding ones. The ones before vk. Okay, so either the given vectors are linearly independent, or of course they are dependent, and in that case some vk will be, preceding ones means vk minus 1, some vk will be a linear combination of the vectors that come before vk in this list. If these are linearly independent, then of course there is nothing to prove. Independent, DENT, then we are done. So assume that they are linearly dependent. Dependent means some scalars will exist, an equal number of scalars, n scalars, not all of which are 0, and if you form the linear combination, that will be 0. Then there exist scalars lambda 1, lambda 2 to lambda n belonging to f, not all of which are 0, such that this linear combination is equal to 0. So not all the lambda i's are 0. We are now going to use this fact. So some lambda I here, some of them are 0, some of them are non-zero, maybe all are non-zero, we don't know, but at least one non-zero lambda is there. So in any case, we can find a largest subscript k for which lambda k is 0. After k, lambda k is non-zero after k, that is lambda k plus 1, lambda k plus 2, they are all 0. So let k be the largest positive integer such that k is less than or equal to n and lambda k is not equal to 0. We can then write this equation in a slightly different manner. Then lambda 1 v1 plus lambda 2 v2 plus etc. lambda k vk is equal to 0. If k is actually less than n, then the terms after this term don't appear, because the higher lambda k's, that is whose subscripts are greater than k, they are 0, so those terms vanish, which implies if you manipulate this equation keeping in mind that lambda k is non-zero, you can write vk like this. Minus lambda k inverse lambda k minus 1 vk minus 1. So that's how lambda k is a linear combination of the vectors that appear before it in that list. So after this result, there are the corollaries, which themselves are very important, and they reveal why the notion of linear dependence and independence, why this notion is so important. So we will see these things in the next vector space video, which will come when its time comes. Tomorrow there is Gregory T. Lee's abstract algebra exercises. Day after tomorrow, on Sunday, we are going to have our analysis video. So that means, since those two things are not falling inside that cycle of usual things, so after today's video, the next natural video in that cycle will appear on Monday. Okay, so today is, what is the date today? 11. So that means 12, 13 on 14th. So on Sunday, on Monday, we will have Galilean's algebra, and there, because one of you has requested for a slight change, so that change will be incorporated. Along with the usual group theory exercises in Galilean, we will start part of ring theory, chapter 16 that is. You actually requested this. So that will be all today. So see you in the next video tomorrow with Gregory Lee's abstract algebra exercises. And one more thing, there is no need to call me sir or anything like that. It sounds very extremely formal. It should be a friendly environment. It should not look like I am a teacher and you are students. That's not the case at all. Because for me to be a teacher teaching these things, I should know about these things far more than I know currently. Okay. So the view should be that we are all struggling with these things to know them as best as we can. So not this, but if you really want to call me something, you can call me this. Okay. सर मत बोलो सर, थोड़ा सा शरीफ लगता है सुनने में. So with that, I end this video. If you want to say something about these things, you can write in the comment section below. So see you in the next video tomorrow. So this is me, Lucifer, from a mathematical room. Have a nice night.